Hi everyone, my name is Clayton Larson, and today I'll be discussing my thesis on assessing the viability of polymer recycling in drag-reducing flows. And my thesis advisor is Dr. John McLaughlin. In our research, we study polymer drag reduction, and this is a phenomenon that was observed way back in the 1940s, and this is where small concentrations of very large, high molecular weight polymers can increase the flow rate during turbulence. So several pipelines, such as the Trans-Alaska Pipeline, use this effect to increase the flow rate of their oil. And farming is an example of an industry that could use this effect, but currently does not due to cost. So any kind of polymer recycling method would be very attractive to them. Our research problem has two different parts. First, we want to identify the factors for maximum drag reduction, because still very little is known about how this mechanism actually works. And secondly, we want to assess the feasibility of a polymer recycling method. So our hypothesis is this. If this is a cross-section of a pipe, and we have a wire that's running down the center of the pipe, and we also have our solution with our polymers flowing through the pipe, we could apply a positive voltage to the wire and a negative voltage to the pipe, creating this electric field that pushes the polymers to the walls. And in this concentrated region is where we would target for polymer recycling. So in our experiments, we have a tank that holds our solution on top of this wooden framework. The tank then drains down into the copper pipe, which is connected to the negative terminal of our voltage source. And inside we have a wire that's coaxially aligned that's connected to the positive terminal, and that creates this electric field. At the exit of the pipe, we have a bucket that collects the solution, and then we use that solution again by putting it into the upper tank for further trials. We zoom in here a little bit. You can see that this tank that is connected to the funnel, and the valve then controls the flow rate. And right here, where our wire enters the pipe, we've implemented a 3D printed wire center. And that actually has a slanted chamber, so the wire enters through and then gets drawn down through the center of the pipe. And at the bottom, we have another wire center. The wire comes down and is then pulled taut to eliminate any kinks, and that creates a nice symmetric electric field. We also have a flow separator for when we want to target that outer flow for recycling. And this is implemented by a slicer that separates that outer red flow from the inner blue flow. And so we've actually got some interesting results from this. In nearly every experiment that we run, we see an exponential decrease in our drag reduction. And due to our literature review, we found that aggregates may be responsible for the drag reduction effect. And it's possible that the aggregates are breaking up because we're using the solution again and again. And if they break up, they reduce their effectiveness. So to test this, we created two identical batches. And in our first batch, we see our decrease, which is what we expect. But now in the second part, the aggregate theory expects that the second batch should return to this initial flow rate value. However, you can see that it does not, and it actually continues this decreasing trend. So this implies that the decrease depends something associated with the pipe, or it's possible that the solution degrades over time, regardless if it's been subjected to turbulence or not. We've also studied the effects of applied voltage to our flow rate. And the important takeaway here is that at 0 and 50 volts, we see that decrease that we normally expect. However, at the higher voltages, we don't see this decrease. And so it's possible that the stronger electric fields could mitigate our decreased drag reduction. And lastly, with our prototype flow separator, our recycling method wants to target this outer 10% of the flow, but current data puts this number more at 40% with our current prototype. And so you have to remember that this is turbulent inside here, and so a lot of this inner flow is actually coming out into these outer chambers, and we're collecting it in our outer flow. So this can hinder any possible recycling method that we implement. So as for our conclusion, the role of the aggregate in polymer drag reduction is still unclear, and we need further theoretical modeling, which is planned to clarify this. We do observe that stronger electric fields mitigate this decrease in drag reduction though, and a future experiment with a smaller diameter pipe is expected to support this theory. And lastly, a thinner slicer may provide better results and get that number from 40% closer down to 10%. And we've also seen in preliminary data that suggests that the aggregates are on the order of a couple hundred nanometers. And it's possible that that could be recycled through a filtration, through a filter. And so, but there still is a lot of data that has to be collected to fully confirm that polymer recycling will be feasible. And so with that, I'd like to thank my thesis advisor, Dr. John McLaughlin, and everybody else here that was all very instrumental in the success of this project. And I'd also like to thank the honors program for funding this research.